So, good morning, my name is Tatiana Toro, and I've decided what we're going to do is I'm going to tell you a little bit. I was looking again at the title I had given, and the title kind of talks a little bit about my trajectory. So, I started doing geometric measure theory and really variational problems, and in fact, the first thing I did, my thesis, came out of was a question that arose when I was looking at the Wilmer functional and is the solution to the Wilmer problem, the one that gave rise to the program that happened here this year. And then from there, I was a grad student at Stanford. From there, I came here. I did a number of stops. I went to Berkeley, and then after Berkeley, I went to the University of Chicago, where I had a great mentor, Carlos Koenig, from whom I learned a lot about PDEs on non-smooth domains, okay? And so just by sitting at I introduced myself, Margaret, don't worry. And just by sitting in his class, somehow a natural question arose that put together what I had learned before from the things he was doing, okay? And that led to learning about uniform rectifiability, something else that's in the title of my talk. So the way somehow the title makes me think of all the steps, let's say, that I have taken to get where I am mathematically and from the research point of view. And now let me tell you a little bit about why did I choose this topic rather than another one, and where the motivation from what I'm going to talk about is. So a couple of years ago, when I was teaching a class and I wanted to teach the theory, the regularity of perimeter minimizers, I will explain what all of these is, using a book by Francesco Maggi, which it was a book that I wanted to read. And there's no better way to read a book than to teach a book. So, so I started, and I got to a point, we will get to that point, and then I continued the book thinking, wow, but wait a second, maybe this thing that I did, in month 2 could be used somewhere else. And suddenly, even though I was teaching the class with a goal, I kept on thinking, but maybe this could be used in another area that I was also working on. And at the time, Zihue was sitting in the classroom, and another one of my students, Max Gehring, was there. And so what I did is, as a homework, I assigned to them to look whether these other things I was thinking about were really, and I will tell you what that is, that's the topic of this class, will work. And so that led to a collaboration between the 3 of us and 2 other people, Simon Bortz, who's currently one of my postdocs, and Max Engelstein, who I met initially as a grad student, who will now be becoming an assistant professor in Minnesota. So at some point, so what I'm going to tell you initially is very classic geometric measure theory. And then at some point, we're going to switch into something that is an application of very classic geometric measure theory motivated by a completely different problem. Okay? So that's how these lectures are going to go. I understand that there's lots of different backgrounds. So I will make an effort to say, for those of you who have this background, every time I say this is what you should understand. And for those of you that have this background, this is what you should understand. And don't worry, I'm going to make a very big pink table so that you can see how to do the translation, okay? If I say these, you understand these, or if I say these, you should be understanding these, okay? So that we're all in the same, we can all understand, and we'll explain how that makes sense, even if it seems a little bit strange. Okay. The other thing is I really, really welcome questions, okay? It's very difficult for me to gauge where you are if you don't stop and ask me. I welcome stupid questions. And when I say that, I know everybody's thinking, oh, I would like to ask a question, but that's a stupid questions. I don't think they're stupid questions. And most often when you're thinking of that, there's 2 or 3 people in the room who are thinking of the same. So please do interrupt me. It's the only way I know where we're at, okay? I mean, sometimes when I know people, I can see their facial expression and try to guess they're lost, they're bored, or they're thinking of something else, but I don't know most of you, so I cannot guess what your facial expression is telling me, okay? So please do interrupt me. If you want, I can pause and do a 30-second silence. They're super long. 30-second silence are super long so that you come up with a question, okay? Questions? No, but you never know. Okay. So, disclaimer, first time I use my iPad as the main place where my my notes are. So let's see if it works or if I have to be pushing it to turn it on.
Very great.
No, it's gonna work. I actually thought of bringing the paper copy because I of course have the paper copy, and I decided it was gonna work, and that's okay. Okay?
I don't do this in Hungary.
Oh, but I'm not going to plug them in. No, plus the notes are in Zihu's computer, were there to be an issue. So, I mean, I have a backup. So, the motivation for all of these, when we come back, is the Plateau Problem. So, what's the Plateau Problem? I'm going to give you a version that we're going to address. But the Plateau Problem, so Plateau was a physicist, and here is the Plateau Problem. You have a curve in space. Okay, imagine your curve. I'm not going to draw it because your imagination is way better than my picture. And you would like to find the surface with smallest area that has this curve at its boundary. Okay? Okay. So let me put this in a setting where I can draw the picture and how. So one way, so this problem has had many interpretations because while you see your curve very easily in 3D and you see your surface, problems arise. I mean, when you think of a surface, are you thinking of a surface like that? Or when you think of the surface, are you thinking of the surface that comes from putting a wire inside soap and taking it out where there's things that are crossing? Okay, so we need to get clear on what surfaces are. Okay, so that was one of the issues that came up in this problem. So the type of problem we're going to look at is the following. So imagine that we have a set. So my open sets are often going to be balls. They're bigger or small. So I have this ball. You yesterday, Zihoe talked about. About sets of finite perimeter. Let's imagine you have a beautiful smooth set of finite perimeter. Here, since my picture is in R2, the perimeter is exactly what you imagine the perimeter is, the length of the thread that you need to go around here. And the question is, can we minimize? I would like to. So that minimization problem I talk about will be find the set E of smallest perimeter that coincides with E0 outside B0.
Tatiana, I didn't define set of finite parameters.
Oh, no, don't worry, I'm going to define that. But we all understand that perimeter is, here the perimeter is, you take a thread, you take your linear, you put it over here, and you measure. That's perimeter, okay, for now, don't worry. Well, no, don't worry. I had imagined that was my turn. Okay, so what do you think that set is? Well, it has to coincide with E0 here. So it has to be this orange piece. And we all know that the shortest distance here, since we're doing this very specific picture, well, the shortest thing is This is a straight line. Okay? So this set E, if this set that minimizes, is going to look like this. And what's the first thing? Because this is the shortest length between these 2 points, and I have to go by there. Does that make sense? Okay, so what's the first thing you notice? Yes?
It's not smooth at those corners.
It's not smooth. So I started with a lovely smooth ball. I put a lovely smooth set, and this minimizer is not smooth. Okay? So imagine that, so you have this problem. It's not, the minimizer exists, I drew it. And it's not smooth. So what we need to do is we always need to start with a big enough class of objects so we can define, say, well, find the one that has minimal perimeter in that class. And clearly, smooth is not it. Actually, these corners are not even C1. Okay, so let me remind you what you did yesterday. Okay, one of the things because we need to, what I'm trying to do is motivate what's the class of sets we have to find. So one of the things you did yesterday was you talked about the divergence theorem. Okay, so the divergence theorem told you that if you have a C1, so if E is a C1 domain, and I believe you maybe talk about Lefschetz also in some sense, but don't worry, we'll come back to these. So let's imagine E is a C1 domain. What's a C1 domain for me is a domain that can be written locally as the area above the C1 graph. C1 means you have one derivative that's continuous, and the divergence theorem tells you that if you have a function, a vector valued function, which is compactly supported in Rn. So C1, one derivative continuous, compactly supported in Rn, and is vector valued. And you look at the integral of the divergence of phi. Well, that is, with a plus, the integral over the boundary of phi dotted, this is the inner product, nu of phi, d, the surface measure. And what did you call the surface measure yesterday? Sigma of HN minus 1? Sigma. Sigma. Okay, so, and who is this guy? So, this is E, and this is nu of E. Okay. So let me define perimeter. Maybe you did yesterday, but so now I'm an Rn, so it's the equivalent of that. Perimeter in one dimension is the length of the thread. In 2 dimensions is the surface area. In 3 dimensions is the volume, and so on. So how will we go about finding the, so I'm staring at these and I'm telling you I'm going to get the perimeter out of here. Okay? So let's see. So this is the unit normal. Outward. Unit normal. So unit has length 1. And the way we find the perimeter in some sense, okay, don't write these because it's in some sense, is if we were able to put a 1 here, this is telling me what the total surface measured of this boundary is. Okay, and that's the perimeter. So this is a compactly supported thing, so 1 is clearly not compactly supported, 1 is not vector value, but you know, so, but if I were able to look at, so a way to find the perimeter, if I were able to look at the following quantity, the sup over phi of all C1 with compact remember, this is a vector valued thing, so this means I take the sup, okay, And this means the sup of phi is less or equal than 1. If I were able to do that in here, I'm not going to prove that, but I hope you I'm going to try to convince you. So if I take vector values, nu of e is basically, since I am on a C1 domain, let's imagine the C1 domain is bounded. If I were able to replace these by nu of e, this will give me a 1, and then I will have the total surface measure. Okay? And that's what happens. This is exactly this in the case total surface measure. Okay. Questions? Yeah.
First stupid question of the day. What's a domain?
A domain, thank you. A domain is an open set which is connected. Okay. So sorry. So and so open in the sense of a metric or a topological space, and connected means any 2 points can be reached by a curve. Yes.
Why do we get the total surface area and not the perimeter?
Oh, because it depends on because it's the same thing for me in some sense. And because very soon for me this will be the perimeter, but I was imagining that if you were thinking of smooth objects, and if I tell you the perimeter of a sphere, thank you. So if I tell you the perimeter of S2, the sphere, I don't want you to think of, the waist of the sphere or whatever that is. I want you to think of the whole surface measure. So perimeter, when we talk in English, perimeter is a one-dimensional sphere. Very soon in this room, when I'm talking, the perimeter will be the surface measure. But I just wanted for once, this is the familiar thing.
I mean, I suppose my question was more along the lines of why do we get all of E and not just the boundary of E?
Oh, sorry. You are absolutely right. No. We get the boundary of E, of course. And there you caught me is because that's if I will call the P of E, that's the perimeter of E, your total surface measure of boundary of E, and that's what we call the perimeter of E. Thank you very much for your question. Okay. So what was the point of these? To hopefully convince you that if I look at this quantity here, the sup, I somehow find the perimeter of the set. Okay, I stared at this. It's a little bit of a problem because I'm always trying to think, okay, I need a large enough class. So what happens? When you look at these, you can only write this expression in a domain where you have a unit normal at the boundary and a well-defined surface measure. Okay? Because this is what I wrote. So that's a pain. I cannot do that. I need some degree of smoothness to do that. Okay, now let's go, but this board says that this is the same as this. And this expression I can write in any set E inside Rn. So this one is perfectly fine. Okay? So that is the motivation for, so remember, we started with that picture. We noticed that even for a smooth domain, the minimizer is not smooth. I'm trying to find a large enough class where I can define this problem. I'm about to introduce it. Okay? And the introduction comes from this remark and that remark. Okay? So definition. Okay, first place what I want to make a disclaimer of if that's already too much information, you can discard this piece of information. I drew a bounded domain here, I drew a bounded domain here, but I might in some cases be interested on this, and it goes over there. So this is not going to have finite perimeter because it goes all the way over there. So I mean, but I can be interested in this, in what the sort of thing I do here. We only look at local properties. So I could be talking at sets of locally finite perimeter where I only look at what happens on balls. Okay? And so that I will only be interested on what happens on balls here. Okay? So I'm going to define what happens locally, but if you don't like that distinction with the whole thing, remove the word local, change the ball to Rn, and we're happy. Okay?
No fractal behavior.
Huh?
No fractal behavior.
Yeah, so that's an example. What's an example? So I'm about to write something, and then I will go to you, I'll answer your question. I mean, I'll ask, when on earth is that what I wrote I'm going to put, if something happens, then blah, blah, blah. And then we'll stop for a second and then think of when that doesn't happen. Okay? Okay, so definition, let's set E and Rn, okay, is of locally finite perimeter. And I want to point out that I didn't write domain, correct? It's not that I forgot. Sometimes it's good to, it's sometimes you never know whether I made a typo, I forgot, what did I really, is there an intention? So is it if locally finite perimeter, let's maybe forget that, if for every ball B, okay? My balls, unless otherwise indicated, will be open. So maybe for the second, let me remind you what an open ball is. When Zihui talks this at some point about covering theorems, that's the only time she's going to write the balls like that, and hers are going to be closed. It's not for confusion's sake, but I mean, it's the way it is. So my balls are open, okay? They don't include the boundary. If for every ball, when we look at this number, the soup, okay, so I take the set E, I'm looking at the left-hand side, divergence of phi dx, and I'm going to look at these among all phis, which are C1 with compact support in B. That's the local piece into Rn. If you wanted a set of finite perimeter, you just put Rn there. So it's C1, but you only look at the fact. So this definition, this is the soup of phi. If this is less or equal than 1. We look at these. I'm going to call these. This clearly depends on the ball. So I'm going to call this C of B just because it's... So a set E is of locally finite perimeter if for every ball B, this guy is finite. Okay? I haven't said what the perimeter is or not. So, as Margaret pointed out, okay, so when on earth, you might be thinking maybe this is finite for every set E that I put there, at least every nice plump set that I put there. Okay, so I will leave it to maybe is a good exercise. I'm going to draw something. And I let you convince yourselves that this set is a problem. Okay? So imagine that E looks initially, step 1, this is E0. Then my next one, I'm going to put a snowflake here, a snowflake here, and a snowflake here. So what's a snowflake? A Van Gogh snow curve. So what I do is this side is the same as this side, the same as this side, the same as this side, and this angle you choose it. Pi over 3 works well. And next, you do the same thing. And if you look at each iteration, since a priori this is an, I think, the perimeter of these shapes starts growing and growing and growing. And when you look at what happens at the limiting set, it's going to be plus infinity. And it's because this curve that you obtain is a curve that has locally infinite length. Okay? So it's very correct that this really removes all fractal behavior in everything anywhere close to it. Okay? Questions? Okay. So let's see. So I am going to assume that everybody has taken linear algebra. Okay. I'm not going to assume that everybody has taken functional analysis. So if you have taken linear algebra, I want you to remember what a linear functional is. A linear function, you know, you go from a vector space to a vector space. And if you have not done functional analysis, take the rest as, you know, when you go on a tour to Europe and you take a short visit to each country. So this is a short visit to functional analysis. Take it. Like, you never doubt your guide, or very seldom you the guide on a tour. Please take this one. This one is correct. Okay. So, but what I'm going to say is I want to remark something. So imagine that I'm going to define L of phi. Okay, is the integral of the divergence of phi dx. So if phi is in a vector space, okay, because if you take two functions that are compactly supported here, the sum is compactly supported here, and if you take a linear combination, it's there, okay? And I claim that L is linear, because if you take sum, the divergence of a sum is a bunch of derivatives, so it's the sum of the divergences, and you separate the integrals, and so this is a linear functional. And I would like to notice, so this constant C of B is when I take my phis that have norm less than 1. But if I have another phi that doesn't have norm less than 1, I simply divide it by the sup. It gives me one of these. So I leave it to you to check that L of phi is bounded by this constant C of B, phi infinity. And so this tells me that L, this means the tour of functional analysis. This tells you this is a bounded linear functional. Bounded linear functional. So it's funny because I start with phi, if you think of it, I start with a phi that's C1. I bound it in terms of the L infinity norm, the sup norm. So when I stare at these, okay, I always want you to, in this class, and this is what I'm about to say in my big pink drawing, when you look at these, nothing tells you that this function phi is C1. I'm only seeing, I only need to be able to talk about the sup. So there's a way to say is a bounded linear functional, and actually the only properties that I see here is that phi is compactly contained, that's compactly supported from B into R. I can extend, what I'm saying is I can extend my bounded linear functional to be in all of continuous functions. And then there is a very nice theorem, is a version of Free's representation theorem. So what this theorem tells you is that when you have a nice bounded linear operator from a nice space, a Banach space, the space of continuous functions compactly supported, you can represent them in a very nice way. Okay? So, please bear with me. If the words I'm about to write are words that you have never seen, I promise the next board will tell you how to interpret them. Okay? So, for a minute, bear with me. Don't stress. I mean, it's just, you know, we'll make it work. Okay. So, theorem. So this is the first structure. So what I'm going to apply is something that's called Free's representation theorem. It's not your, let's say, standard version, but it's basically that. I'm going to call this the structure theorem for sets of locally finite perimeter. And this is, there will be two of those, okay? And so, let E be a set of locally finite perimeter. So you see, we'll start already cutting letters by the end of, you know, the week. This will be an LFP, but, you know. Then there exists one, okay. If you've never seen what I'm about to say, once don't stress, two, you will see it the latest by tomorrow, okay? A non-negative, and also there will be an explanation of how you can ignore everything I'm going to say here. Okay, so some of you, well, anyway. A non-negative radon measure. I'm going to call it for now this, but this notation will disappear. Two, perimeter measurable function. Nu E, okay, such that one, Nu E is 1 almost everywhere. Almost everywhere means everywhere except on a set that you don't see. And 2, and maybe I'm going to put 2 down here. 2, you're not going to be surprised because I cook up everything so it looks exactly the same. This one happens to be, so check it out. I have a function nu, which is 1 almost everywhere. Okay, and so here is what I do. This is phi dotted with nu of v, integrated with respect to this funny measure that I haven't told you what it is. Okay? And this holds for every phi, which is C1 with compact support in Rn into Rn. And the only thing I'm going to do now is I'm going to give a name, because this is kind of cumbersome, so I'm going to give a name. Mu E is nu E times this thing here. Okay, this is called the Gauss-Green measure. these, sorry, when I put an absolute value, I mean just these. This is the total variation or the perimeter measure. Okay? So what have I done? I started with a smooth set. I told you things that you had seen before. I showed that one of the things, one side made sense without being smooth. I forgot that I had a smooth set. I put a definition on the board, and I told you, at least formally, using those words that some of you have never seen and might not see for a while, things look exactly the same. Okay. Okay, so what would I like you to do? And so I understand that radon measured is not something you've necessarily seen. Measurable functions is not something you've seen. So here is what we're going to do. I'm going to make a table here. First of all, don't panic. Okay? I know very well that I know you're more or less where you come from. I know that half of you are undergrad, so I don't expect you to do any of these. What I'm going to do is I'm going to put on the board how do you, the translation. Okay? So I told you this is like a tour of Europe, and here is your cheat sheet book of the translation in some of the countries that you visit. Okay. And I really